So I have my 5 books again. If you're listening to this, you'll have to imagine I have the 5 books. And I want to arrange them on my bookshelf, but I only have room for 3 of them. So how many ways can I arrange these 5 books if I only take 3 of them? So we would start off probably by going to the fundamental counting principle, right? So we have 5 books, 5 different books. And we want an arrangement of 3. So using the fundamental counting principle, I would say, well, I have 3 slots, right? 3 slots. Let's use those 3 desks there. So how many choices of book do I have to go on this first desk? I have 5 choices. Okay, so take one of the books, put it on that desk. How many books are left to go on the second desk? There are now 4 books left. And how many books are left to go on the third desk? 3. And 5 times 4 times 3 is 60. Right? So there are 60 different ways that I can arrange 3 of these 5 books. 60. Now, this thing happens a lot in mathematics, or in doing these arrangements where we have a number of distinguishable objects, but we don't want to arrange all of them. We know how to do that, right? If I arrange all of them, it'll be 5 times 4 times 3 times 2 times 1, which is 5 factorial. So we did that the other day, factorial notation, 5 factorial. But if I want to arrange some of them, then we have a special notation. And it looks like this, NPR. And it's the number of permutations of n objects taken r at a time. So it's the number, and you remember what a permutation is, right? It's an arrangement of distinguishable objects. So the number of permutations of n objects taken r at a time. And it's so important, there is even a key on your calculator for it, right? There's an NPR key. Or actually function, I guess. So on your calculator, what you do is you go put in, well, okay, let's, hang on, I'm going to pause, grab a calculator. So NPR, so you start off with n, right? I want 5p3. So in this case, I want to do 5p3. So on the calculator, we'll go 5. Okay, hang on, we'll go 5. We go to math. I want to get over to PRB, which now I can go 3 to the right or 1 to the left. So I like going left. And it's number 2. You can either hit a 2 or a down arrow. So 2 will be faster because it'll just bring the function right in. So 2 and then 3. So we're going 5 NPR 3, right? So the first number is the n and the last number is the r, and you hit enter and you get 60, right? It calculates it for you directly. Now you do have to know the formula. You do have to use, be able to use the formula, but you can also use the key on the calculator. All right, so while we're at it, so what's NPN? Well, we got the formula, right? The formula is n factorial over n minus r factorial. In this case, r is equal to n, right? In other words, we're going to arrange all the objects. So what's like 5p5? Well, we know what 5p5 is, right? If I want to arrange all 5 objects, what's that equal to? In factorial notation, 5p5. Or I want to arrange 5 objects, that's 5 factorial, right? So that means that 5p5 must have to be equal to 5 factorial, because this is going to be equal to n factorial over 0 factorial, which means that 0 factorial must be 1. So 0 factorial is defined as 1. You can even plug it into your calculator. You can go 0 and the factorial, and it will come out as 1, right? Because it's by definition. So this formula can work, right? So if we do 5p5, that's equal to 5 factorial, which is 120, right? So if I just bring this back down and replace that with a 5, come on, replace that with a 5. Why have you stopped working? Then you get 120, right? Which is the same as 5 math. Really? Come on. Hey. Left arrow to probability, 4 is factorial. Enter. Same thing, right? So 5p5 is the same as 5 factorial, right? If you're arranging n objects n at a time, so you can use the NPR all the time, right? Or, you know, you can use factorial notation. They'll be distinguished on a test because sometimes it'll come out in factorial notation, sometimes it may come out in permutation notation. Okay, so a question could be asked without actually calculating the value, but just saying, you know, so-and-so is going to solve this problem. Here's one of their steps in the solution. You know, is this, which one is correct? Right? And you get like 5p3 and etc. Okay, so you'll have to know the different notations. Okay, let's do some stuff with this. What are we going to start with? Let's see. In some unknown country, vehicle license plates consist of any 2 different letters let's go with English alphabet letters. Followed by 4 different digits. How many different license plates are there? And what we're going to do is we're going to solve this 2 different ways, right? Just to show you there's more than one way to do these things. And you know, again, on a multiple choice diploma exam, they can't necessarily force you to do a particular way, but they can, because instead of giving the answer as a number that you can work out, they can give you expressions, right? And say which of these expressions would be used to calculate it. So if we use the fundamental counting principle, so A, use, then we're going to say, okay, I've got 2 different letters, so 1 letter, 2 letter, and then 4 digits. 1, 2, 1, 2, 3, 4. So I have my 6 different blanks. So how many choices do I have for the first letter? English alphabet. 26. How many choices do I have for the second letter? If it's got to be a different letter. 25, right? There are 25 letters left that are different. How many choices do I have for the first digit? 10. Second digit? Third digit? Fourth digit? That's equal to? All right, we got 26. Hey, it's working again. Times 25, times 10, times 9, times 8, times 7. 3,276,000. So we could have done this first day, right? Counting, just fundamental counting principle. Let's use permutations. Using permutations. Permutations. Okay, how many letters are there in the alphabet and how many of them do I need? 26, so I need all the arrangements of 2 letters from a set of 26 letters, right? And that's 26p2. I have 26 objects, letters, of which I need 2, right? We want permutations, meaning they have to be different, right? Permutations are things that are distinguishable, so they have to be different. Followed by, how many digits are there? 10, and how many of them do I need? 4. So it's 26p2 times 10p4. Okay, let's give that a shot. 26, math, PRB, 2, times 10, math, PRB, 2, 4. And, surprise, amazing, right? It's the same. Yeah. Whoever could have imagined, right? So it works out the same either way, right? So again, right, how can they ask that? Because they can't necessarily force you. They could ask you this question and then just give you answers, right? A, 3,276,000, B, whatever, and different numbers. Or they could give you, 26 times 25 times 10 times 10 times 10 times 10. They could give you 26 times 26 times 10 times 9 times 8 times 7. They could give you 26p2 times 10, and there's also something we're going to learn, which is combinations, right? So they could give you that notation as well, right? And only one of which would, of course, be correct, right? But it's a notational way of solving things, so you have to know how to do this different ways. Okay, what's next? Let's say, in how many ways can the letters so imagine that we have some Scrabble tiles, and you have the letter O, R, the letter O, the letter R, the letter A, the letter N, the letter G, the letter E, and the letter S. And you have to figure out how many arrangements there are, and we're going to throw some conditions on there, right? So it says if, and we'll do a couple of different, 3 different ways of looking at it. If A, there are no restrictions. Okay, so if there are no restrictions, you are free to use the fundamental counting principle, right? In which case, how many letters are there in oranges? 7. So you could go 7 times 6 times 5 times 4 times 3 times 2 times 1. You could say I'm arranging 7 objects. So you could say, so we've got 1, 2, 3. Right? So you could go 7 times 6 times 5 times 4 times 3 times 2 times 1, which I believe is 5,040. You could go 7 factorial, right? Just using factorial notation. And you could also go 7p7, which is 5,040, right? So you have 3 different ways that you can solve this particular thing. If there's no restrictions, I can use the fundamental counting principle, put out my 7 blanks, fill them in with my choices. I could just say I'm arranging 7 different objects. That can be done 7 factorial ways. Or I can use permutation notation and go 7p7. B, the first letter must be an N. Well, we could do this 3 different ways, right? I could put down my 7 blanks. How many choices do I have for the first letter? 1, right? There's only 1 in. So there's restriction here, right? We always got to deal with restriction. So there's 1. Second letter, how many choices? And then 5, 4, 3, 2, 1. Which is, what? 30, 120, 720 or something? 720. I could say it's 1 times 6 factorial, right? So I'm going to take care of the n and then just arrange the other 6 letters. So I go as 1 times 6 factorial, which is also 720. Or I could say it's 1 times 6p6. Right. In essence, you can sort of, you can discard the n, right? Forget about the n, it doesn't matter, right? It's out of there. I now have to arrange 6 objects. Okay, and that can be done 6 factorial ways or 6p6 ways. And the vowels. O, R, A, N. Okay, what if the vowels must be in order? Vowels must be in order. So what we have to do now, we got a sort of a special case we have to deal with, right? We got to say, I've got the letters. Well, okay, if they got to be in order, I guess really it's what, A-O-E, A-E-O. So what I'm going to do is I'm going to treat the vowel, right? If those are on Scrabble tiles, I'm just going to kind of glue them together, right, in order, A-E-O, and treat them as one block now, right? So if they've got to go in order, then they're one thing, and I now have 1, 2, 3, 4, 5 objects to arrange. Okay? So the vowels must be in order, and let's say and together, I guess. We better and together. So together in order. So I glue them together, right? So they're now one tile, and I now have a total of 5 tiles. I've got the tile that says A-E-O, and I've got the tiles that say R, N, G, and S. And so those can be arranged in 5 factorial ways, or 5p5, right? Either way, which is, I think, 120 ways. Okay, or again, you could do fundamental counting principle. I'm not going to do that so much, right? Because it's just the 5 blanks and then 5 free throws. Let's do one more. What if they've got to be together? So vowels must be together. Together, but not necessarily in order. So I gotta have all 3 vowels together, but they could be A-E-O. How else could they be arranged? A-O-E, E-A-O, E-O-A. How many ways are there of arranging just the vowels? 6. 6, right? Which is what? 3 factorial. Okay? So if the vowels have to be together, but they don't necessarily have to be in order, then I'm just going to put down sort of a super box with the vowels in it, right? And the vowels are going to be separate. And then I'm going to put down the rest of the letter. So how many objects do I have that I'm going to be arranging? So again, 1, 2, 3, 4, 5, right? I got 5 objects to arrange. Okay, so Let's go just stick with factorial notation. But the vowels can be arranged how many different ways? Or sorry, permutation notation. How many ways can I arrange the vowels? 6, which is 3p3, right? So we're going to go 5p5 times 3p3. So this is saying you're arranging 5 objects, right? One of those objects is the box that has vowels in it, right? And it can either go first or second or third or fourth or fifth, right? There's 5 different places it can go. That's the 5p5 thing. But every time I put it somewhere, it could be AEO, it could be AOE, it could be, so every time I put it somewhere, it can be arranged 3p3 different ways, right? And so that is equal to 720. So there's 720 arrangements where the vowels are together, but not necessarily in order, right? So we've got to sort of box them up, treat them separately, right? Just like fundamental counting principle, when we deal with these types of problems, we have to deal with our restrictions first. Well, what are the restrictions? Well, this has to be, together. So together and in order, all right, then that's just one thing, right? You just glue them together. They're in order. There's only one way to do that. Be together, but not necessarily in order. Oh, okay, we've got 3p3 ways of doing that. All right. What else do we want to do? Next page. In how many ways can 3 girls and 4 boys, 3 girls and 4 boys be arranged in a row if no 2 people of the same sex can sit together? Okay, so we got a row of 7 desks or whatever, right? Or we're going to stand people up. We're going to say, wow, so 7 chairs. We've got 7 chairs. There's 7 people. They're a club or whatever. We want to take a picture of them. We want to sit them down, but we don't want to have 2 boys together, 2 girls together. So how many ways can we arrange these people? So how's the arrangement going to have to go? Boy, girl, boy, girl, boy, girl, boy, right? Because there's 4 boys. If we start off with a girl, we go girl, boy, girl, boy, girl, boy, and then we've got another boy. So we can't start that way, right? So we have to go. So in doing a fundamental counting principle type of thing, you would list the 7, 1, 2, 3, 4, 5, 6, 7. And you would say boy, girl, boy, girl, boy, girl, and we got 1 more boy. I don't really count to 7, I only rate 6. Fundamentally, I don't count all that well. Okay, so how many boys are there that can go in the first boy spot? 4. How many girls are there that can go in the first girl spot?
3.
How many boys are there that can go in the second boy spot? How many girls are there that go in the second girl spot? 2. What's next?
2. 1.
Okay, what's that work out to? 144? I'd say that's gross, but you'd have to know that a gross is a dozen, which is 144. In which case you would laugh, but otherwise you wouldn't. So. How else can we do this, right? We can say, I have 4 boys, and I've got to take all the permutations of 4 of them, right? And I have 3 girls, and I need all the different arrangements of them. And I guess we're assuming there are no identical twins in there, because they need to be distinguishable, right? So if there are identical twins, then they need to be dressed differently, so we can always call them apart. Yeah, something. Yeah. They need to be distinguishable. And what's 4p4 times 3p3? 144. I know, it's shocking, isn't it? Okay. What if? You want to go get it? Yeah. So stop me at any time because I'm just going to keep going, right? So, what if there are 6 actors and 8 actresses available for a play? With 4 male roles and 3 female roles. How many ways can we cast the play? One of the questions you got to ask yourself, not now because it's permutations, but at a later date, one of the questions you have to ask yourself is this a permutation? Are these things distinguishable? So do you think, are the roles distinguishable in a play? Usually, right? You know, unless you're guard 1 and guard 2 and you don't have any lines and that. But assuming you've got lines and that, you're playing a particular role or a part, that's a distinct thing. Okay, how many ways can we cast the play? So how many actors are there and how many do we need?
8.
How many actors are there?
6.
So 6. P4, right? We want all the arrangements of those 4 actors from a group of the 6 actors. And for each of those ways, right, how many females are there?
8.
And how many do we need? Okay, this gets a little bit easier than starting to write down like 7 blanks and filling them in and all that good stuff, right? So we just start to say, okay, look, we've got 6 actors, we need 4 of them. That's 6P4. We have 8 actresses, we need 3. That's 8P3. We need to multiply those 2 together. And what do we get when we do that? $120,000. That's pretty big, right? It's kind of amazing, when if you stop to think about this instead of just, okay, whatever, move on. If you stop to think about it, it's wow, like, there's like 3 million different baseball lineups that you could have. There's like, how many different milkshakes you can have with Peter. Like, by putting things together in different orders, by choosing them, there's a lot of different ways that this stuff can happen.
Can you just show us how to do it on the calculator?
Yeah, you punch in 6P4 and then 8P3. You have to watch the video, man. Come late, pay the price. Okay, what have we done? We've done that. We got we've done one of those. Okay, so Student Activity Council sold 200 raffle tickets. How many ways can we draw first, second, and third prize? Okay, our first, second, and third prize distinguishable. Yes, right? As opposed to, if there's 200 tickets, we're drawing 3 to win a ticket to a movie or something, then it really doesn't matter, right? Okay, and again, we move into that in a couple of days, but I'm just foreshadowing, just letting you know that there are other ways of doing this, right? There are other ways of drawing 3 where, okay, we don't really care, right? It's just, you 3 are going to the movies, great, right? But if you win first prize, you win second prize, you win third prize, that's a distinguishable arrangement, that's a permutation. So what are we going to write down? 200 P3, right? So on our calculator, what will this look like? 200, math, over to PRB. Number 2 is NPR, and a 3. So 7,880, what was the last one? 400, thank you. Almost 8 million ways. Okay. In a few days, we'll look at 649 and figure out why we shouldn't bother buying a ticket, but we can't do that just yet. Because in 649, does it matter what order you choose the numbers? No, right? It just matters that you have. What if it mattered, right? How many numbers are there in 649?
649.
There's 49, and we need 6. So what if it was a permutation? What if it mattered the order you chose, right? So you had to say, this is the first number I'm picking. Right? So it didn't come out just sorted. If you buy a quick picker, that it just comes out sorted in numerical order. But what if it was a specific order and you had to have that? What's 49p6? E what? 1.006 times 10 to the 10th. So that's like 10 billion-ish. Right there, 10 billion. That's, you know, double the number. Well, it's not quite double the number. 1.5 times the number of people on Earth. You know, so there are 10 billion permutations. If the order mattered, right? We're going to look at it next week. We'll look at it and say, okay, what if the order, not next week, right? Later this week, we'll look at it and say, what if the order didn't matter? Because it doesn't matter, right? Because if it did matter, nobody would have won yet. Too many, you know, no matter how many tickets were sold, you know, there's 10 billion possible combinations that, or sorry, permutations. That would be tough to do. Okay, so most of you are probably heading off to some post-secondary thing, and you're going to be given a student ID number. And let's say that the student numbers at a college are 7 digits. I was trying to recall my ID number from UOC to see if it was 7 digits. But I can't remember back that far. No, at one point I did know it. I'm sure I do too, but okay. So student number is 7 digits long and cannot okay, so they can't start with a 0, right? They're not going to start with a 0. Usually there is some logic to how they start. Like your ID numbers. Do you know how your ID numbers? Well, your ID number says something about you. So somebody give me an ID number and I will tell you what it is. I mean what it means. 995 04
0001.
I mean, you were born in 1999.
No.
You started school. You started school in 1999. Is that what that means? I started school in.
Somebody give me another one, just because I need a couple. Or like
095
095 33
2503.
25. Okay.
Yeah, that's what I just said.
Are you sure it's 99504?
That'd be my school ID.
I'm just guessing you're rusty.
Really?
I'm pretty sure.
No. Sorry.
I'm pretty sure it is.
Somebody give me another one.
Oh, I'm wrong. I'd be 095.
095
28
28.
6004.
Okay. I don't think that's right. Sorry.
That's my ID. I'll
Really? Show it to me.
I will.
5095.
Mine starts with 995. Just because it doesn't start.
Okay, yours start with 995? Really?
Mine's 496.
Mine says it's
995 278.
502.
Did I say born? I didn't mean born. It starts with.
Oh, okay, sorry. Yeah, you know what? Never mind. Yeah, you're right. I'm looking at the wrong digits. Okay, I don't remember this anymore. Okay.
Yeah, 95 is the year.
Yeah, right. Okay, so the first digit is the year that you were first registered in the CBE. It's the last digit of the year that you registered in the CBE, right? So it could be like 2000, 2009. Like if you're new to the board, you might have a later one. The next two digits are the year you were born. The next three digits are the day of the year. So this is the 286th day of the year. This is the 332nd. So somebody here was born like late November, right? Who has the 332?
Oh, that's mine.
That's
oh,
yours.
sorry.
When's your birthday?
November, late November.
Late November.
Yeah.
Good enough, right? 278, same thing, right? The next digit, the 5 or the 0, it's 5 for girls and 0 for boys.
I'm 27.
Okay? And the last two digits are which student you are that registered that had all the other information the same. So for example, so this is Jen, you are the third girl registered in that year who was born that day, etc., right? And somebody is the fourth, and somebody's the first, and somebody's the second.
I didn't know that.
And some numbers, right, so that's neither here nor there. So here's the 7-digit college number. We're just going to assume it can't start with a 0. So if digits can be repeated, how many different student IDs? How many different student numbers are there? How many? Okay, how are we going to do this? If in doubt, fundamental counting principle usually works pretty good, right? How many choices do I have for the first digit? 9, right? Can't be 0. So there's a restriction, right? First digit cannot be a 0. How many choices do I have for the second? Third, fourth, fifth, sixth, seventh. Okay, so how many? There'll be 9 million, right? 9 times 10 to the 6th. What if digits cannot be repeated? Okay, fundamental counting principle always comes in handy here. How many choices for your first digit? Okay, so it still can't be 0, right? How many choices for your second digit? 9. Why 9? Yeah, we already used one, right? So we can't repeat. So we know it can't be 0. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Then what happens? Well, you've used one of those, but now 0 comes back into the pool, right? If they're on the numbered balls, we've taken the 0 ball out. We've drawn a ball out, right? That left us with 8. We put the 0 ball back in. We've got 9, and then. Okay, and what does that work out to? Okay, so like your student numbers, we're going to say if the student number starts with a 3, it means the student registered in 2013. How many student numbers are available if no digits can be repeated or may be repeated? Before we do that, let's go back to the other one and take a look at it, see if we can do this a little bit simpler way, right? So if for this one, if digits can't be repeated, we know we've got 9 for the first digit. Then after that, we have how many digits available? We've got 9 digits remaining, right, that are available, and we need 1, 2, 3, 4, 5, 6. So we could just go 9 times 9p6, right? Save ourselves some work. Okay, like writing down all the blanks. So let's try this one this way. If the first digit's a 3, it means student registered in 2013. How many student numbers are available if no digits may be repeated? It's going to be 1 times 9p6, right? Okay, so this 1 means we use the 3. Okay, we now have 6 digits remaining. It's a 7-digit number. We've used one of them. We can't repeat, right? Not repeating means we can use permutations. We have 9 digits remaining because the 3 is gone. So we've got 0, 1, 2, 4, 5, 6, 7, 8, 9. And we need 6, so it's just 9p6, which is 60480. Okay, that should do it, I think.